what are Friedman's assumptions? Now, I think there are two types of assumptions that Friedman does not distinguish, which is a mistake. And therefore, it's very hard to understand what's going on. But once you get that, then you get clarity, I guess. And I already, during my presentation of the paper, I stressed one of these. Friedman explains immediately after the given quote, the one with the realisticness, a hypothesis is important if it explains much by little. This is if it abstracts the common and crucial elements from the mass and complex and detailed circumstances surrounding the phenomenon to be explained and permits a valid prediction on the basis of them alone. So this is the passage I partly discussed already. So what he says is that the common and crucial elements that are abstracted, right? So a physical example is the falling ball, whose behavior is explained by recourse to gravity alone, and not other forces or other specific properties of the situation. He makes a little, well, he doesn't know the physics well enough because there's an additional element in there. This is now here in parentheses, which is in the law of free fall, counterfactually gravitation is set constant along the ball's trajectory. He doesn't know that, right? But if you look at it carefully, gravitation has changed. So, but in the law of free fall, you put gravitation constant, right? You say, it's just, the G is just 9.81 meter per second square, right? It's constant, and then no other forces, no friction, no electromagnetic forces, no wind, nothing, right? So it's an idealization. So this is what he says. So, and that's an important hypothesis in that sense because it abstracts the common and crucial element. This is exactly what it does. The common and crucial element in all these free fall and similar example is gravity. You can set it constant. Forget about the variation. Forget about the other forces. That's the common and crucial element. So this is what he means here. An economic example is the fact, say, of a tax increase on retail prices on cigarettes. Right? This is the example that I mentioned already. It comes from Marshall there, which can be explained by recourse to the competition of firms alone, thereby abstracting from all other factors. He's saying, if you want to understand the phenomenon, go to that factor. That's the leading one. That's the force that explains almost everything about it. Right? And Friedman continues then, to be important, therefore, a hypothesis must be false in its assumptions. Namely, the assumption that the assumption being the firm is in perfect competition, which is false. But the as if you use it, the firm behaves as if it in this situation, then you get by this very simple hypothesis an explanation for the behavior of the firm, right? And you have abstracted from everything that's not really so important. That's the leading factor. Like in the gravitational example, you can even abstract from the variation of gravitational force, just take gravitational force in idealized form, and then you get already the right result. The falsity consists, therefore, in idealizing the most relevant factor. Idealizing is one thing in the gravitational case, constant gravity in free fall and perfect competition in the cigarette case, but that's not the only element. The other element is abstracting from all the other factors that are part of the real situations. So you're doing two things when you look at it from the point of economic theory or physical theory. You idealize the relevant factor, the most relevant factor, and you abstract from everything else. So in the case of firms, you say, I treat these firms as if they were in perfect competition, and that does the trick for a certain set of problem situations, not for all of them. It works for tax increase, doesn't work for other things. So Friedman continues, the relevant question to ask about the assumptions, now these are these idealizing, and abstracting things. The relevant question to ask about assumptions of a theory is not whether they are descriptive realistic, for they never are. Yes, they are not, because they are abstraction and idealization. It's not their purpose, right? But they never are, but whether they are sufficiently good approximation for the purpose at hand, meaning for the concrete situations you want to apply it. So the only question is if you ask, is the assumption of that of vacuum a good assumption? Well, it depends whether it gets good prediction. Is the assumption of complete competition, a good perfect competition, a good assumption? Depends, right? Got to look at it whether it's explanatory or not. And Friedman continues, and this question can be answered only by seeing whether the theory yields sufficiently accurate predictions. It's not the analysis of the theory itself, but only the predictions you can see there, nowhere else. Thus, a concrete situation is treated as if only a few, even idealized factors were present, which is descriptively false. Right? In the free fall case, there are other forces present. Gravity isn't constant. It's all false descriptively. Right? But it's analytically strong because it analyzes, it tells you what are the leading factors, the really relevant factors, which you can see then by the correctness of the predictions. And this procedure is justified by sufficient predictive success. That's the idea. So as a scientist, you look at the situation, analyze it, look what is important here and what is unimportant, and how can I idealize the important things such that they are treatable, right? Such that I can build a theory. For instance, write down an equation, which is not too complicated. Thus, a concrete, complex situation as is treated as if it was a drastically simpler situation, as star. Right? This is this as if methodology. Clearly, as a description of as is utterly false. Right? Describing this falling situation. Here is a vacuum, and there are no other forces. Then a constant gravitation is all false. It's just false. There are many other forces. Gravity is not constant. It's just false, descriptively false. So, but that is we use, and the use of S star instead of S is justified by the fact that it can be scientifically treated. So the equation of free fall is very easy to integrate and calculate then. For example, can be exactly described in mathematical terms. You can write down the equation, whereas for the complex stuff, you don't know what the equations look like, and it yields sufficiently good predictions for S. So U replies S by this idealized, changed S star. And therefore, and now this is important, the specific falsity of S star may be called falsity due to abstraction and idealization. These are the cases, the most of the cases that Friedman describes are of that type. You idealize and you abstract. Right? In the cases of the firms, you say competition plays a role, but I idealize it to perfect competition and I abstract from all the other factors. So it's a very, very specific falsity, and this is what has not been seen in the literature for reasons I don't understand. It's a very specific falsity that Friedman claims. That's the falsity due to abstraction and idealization, but that's only the first type. There's another type also in place, and that's then confusing perhaps. In this case, the degree of falsity of S star can be decreased by adding corrections which partly revert the abstraction and idealization. This is not in Friedman, but this is when you know other disciplines. In physics, for instance, there you can, if you have the law of free fall, you have the abstraction and the idealization, and you can revert that. For instance, you can say, okay, I don't set the gravity constant, but I take into account that gravity changes. We know the law, we can calculate it from Newton's law, and then you can revert the abstraction. Or you can say, in the case of that fall, if the fall is longer, then you can say, okay, let's add a term that takes care of friction. You can do that. So what you can do is these two steps, the abstraction and the idealization, you can revert by adding corrections. Right? In the mathematicalized sciences, that's typically possible. It may also be possible, I guess, also that happens in climate models. It happens all the time. It probably happens also in I don't know the details, in economics when you simplify and you write down three. Well, we had it already in the when you disaggregate, right? You have an aggregate and then you say, okay, now let's not one representative agent, but let's take three different of them or whatever. You disaggregate and then you get the more equations. That's exactly the same effect, right? First you have idealized in one representative agent and then you disaggregate and then you get 3 or 5 or whatever. So this is a process. So the sign for this technique of abstraction and idealizing is you can revert it by adding corrections. That's important, quantitative corrections. And then you can, in many cases, improve the models. That happened in physics all the time. Okay, this is what I said, and then I come, the next session, I come to the second type. The second type is different from the first type. The second type is now very unfortunate in the sense that Friedman uses this other method of to generate descriptively false but scientifically fruitful situations S star, unfortunately without making the difference to the first type explicit. And that added to the confusion, because if you don't see that difference, and Friedman does not refer to the difference, but you'll see in a moment, that's absolutely deadly for a concise understanding, and people were really confused by that and couldn't make out what Friedman was after. Now, in the second way, the situation S, that's the real situation, is not only simplified by abstraction, but also a relevant factor F in S is substituted by a qualitative differently factor F star that is unreal. That is definitively unreal. It doesn't exist in reality. But you substitute something real by something unreal, and therefore you get a situation S star. Examples will follow in a second, right? This is therefore different. It's a substitution by something unreal. Okay, Friedman's examples are the following. The leaves of the tree, which are treated as if they individually sought to maximize the amount of sunlight. This is the false assumption. It's definitely false. These leaves don't do anything. They just sit there passively, and there are forces working on them, you know, that were developed by natural selection in evolution. So you substitute, and they have no dynamics. You know, the leaves cannot decide or jump from one place to the other. But this is a substitution, you say, by something completely unreal, okay? The other one, the expert billiard player, who is treated as if she solved the relevant differential equations, right? She doesn't. She does not at all. But you behave as if she did. So you put in something completely unreal. She doesn't calculate. And now next to the examples from economics, firms are treated as if they were seeking rationally maximal expected returns. They don't. The managers do something else by their belly, whatever they do it. So you replace something by something real by something unreal, right? F star. Now, of course, you need an argument for that. Now, first you need a motivation for it. And the motivation for the substitution of F by F star by the claim that in the given situation, F star has approximately the same effect as F, but is easier to handle. That's the argument, right? So you can say, if I replace F by F star, I get something that's roughly equivalent concerning the effects, not the nature of the thing, right? But the effects are probably similar, very similar, and we can handle them much more easily than the original thing. That's the beginning of the argument. And then the claimed effect, claimed effect equivalence of F and F star is preliminarily justified by a theory that connects F and F star. So you have a theory that tells you, look, it's quite possible and it's plausible that F star has the same effects than F, right? And you've got a theory that gives you the motivation and preliminary justification. Now, in these cases that we discussed in the three examples, the connecting theory of F and F star is a sketch of selection theory, right? Biological selection theory or some sort of selection theory concerning economics or expert billiard players. So in these, the optimizing effects of selection processes are the same as the effects of rational choice processes, F star, seeking the same sort of optimality. So what you know is that you know that from theoretical economics, that if you do it rationally, then the aim is of optimizing something. And you know from biological selection theory, evolutionary theory, that many possibilities are tried out in evolution, and then what you get by selection is the optimal solution that's available, right? So you've got a theoretical argument why you can replace sometimes results of selection processes by processes of rational calculation. Right? That's the idea. That holds for the billiard player as it holds for the firms, as it holds for these leaves. That's the basic idea. So this is, of course, still speculative. Also, in the second case, the ultimate justification for the substitution of F by F star in S star is that it yields sufficiently good predictions for S. Right? So you make this substitution, is theoretically motivated, you've got an argument why this should be a possible substitution, but the ultimate argument, as always in Friedman, is you've got to find out whether it's predictively valid or not, right? And then you say, okay, So in the case of the billiard player, if you say, if I want to predict how the billiard player is going to play, then I replace her actual thinking processes by solving the differential equations for the balls. I calculate them, and then I will find out, oh yes, the expert billiard player does the same as if she calculated that, but she doesn't. But for the purpose of prediction, that's good enough. That's wonderful. Same holds for the firms or holds for the leaves. So you replace something. You not only idealize it, but you replace it by something completely qualitatively different. That's the idea. And clearly, as a description of S star is utterly false, right? I mean, in the firm, there's nobody really calculating then the returns, the expected returns, on the basis of theory. And therefore, Friedman thinks that also these empirical investigations in managerial behavior are just have the wrong goal, right? And they never will get there where they want to be, because using these assumptions here, these false assumptions, is much more effective. All right. Now, in the second case, the specific falsity of S star may be called falsity due to abstraction and substitution, right? You substitute something. And there's it's a very specific falsity that Friedman discusses here, abstraction and substitution. The first one was abstraction and idealization, right? And that's the difference between idealization and substitution. Now, to see the difference, which is not an absolutely categorical difference, but that's not that important, but to see the contrast, in contrast to the first case, the transition from S to S star cannot be gradually reverted by adding corrections. Right, which you could do, adding corrections was possible in the first case because you abstracted from something and you may add that, and then you have an idealization and you may idealize again, and then you come back to the real situation. So you can gradually revert the falsity or reduce the degree of falsity, but that's not possible in the second case because F star is a qualitatively different substitute for F, right? So you cannot, by slightly changing it, then coming back to F. No, that doesn't work. It's just something else that does the same job. That's at least the assumption. Now, the problem of understanding F53 is that whenever Friedman speaks in general about false assumptions in economics, he refers only to falsity due to abstraction and idealization, and not to falsity due to abstraction and substitution. So when he speaks about it, he refers always to the first type of falsities. So once you want to apply that to the second type, you say, that doesn't work, it's just not right. Right? So what he's doing is that what Friedman is doing, in his mind, he's got only the falsities of the first type, but in his examples, which are necessary to understand what's going on, he also treats the falsities of the second type, but he never refers to them abstractly. And then everything gets confused, right? But the idea is pretty clear. Once you make this distinction, then you see immediately what's happening, and we'll see that in the following. And if you look at when he talks about these assumptions in abstract, these are on my slides here. There you can look it up. They all refer to the falsities of the first kind. So what he's got in the back of his mind all the time is the law of free fall, right? Where you have abstraction and idealization, but you do not have this radical substitution that you have in the other cases, which are extremely important for economics. Now, it's important now, in order to get a wider perspective, to compare that, for instance, with physics. Because the physics case was type 1, right, falsity. And now I'm telling you also physics uses type 2 falsities. It should be noted that also in physics, physics contains not only falsities to abstraction and idealization, first type, law of free fall, but also falsities due to abstraction and substitution, second type. And from that example that I'm presenting to you, we can learn a lot. Also, you'll see that today. The example is that was developed in the 1930s when the atomic nuclei were discovered roughly in the early 1900s, and then people studied atomic nuclei, and then they tried to understand what atomic nuclei do. Now, from our today's point of view, atomic nuclei are mainly composed of neutrons and protons, and there are other particles that glue them together anyway, but they are mainly neutrons and protons. And this is a very complicated problem once you have a larger atomic nucleus that has, then, say, something like 60 particles. and to calculate what the atomic nucleus does by a reductivist procedure, by looking, composing it of these 60 particles, is just not possible, or was not possible in the 30s. So people tried to develop a model of the atomic nucleus that was treatable, right? That you could get properties of the atomic nucleus. But the point was, this is a many-particle problem, as it's called in physics, and that's not solvable. 3-particle problems already are not solvable. 2-particle problems are wonderful. 3-particle problems and above are not analytically solvable. That's the usual situation in physics. Everyone knows that. So what they did is, they said, oh, okay, let's assume a nucleus is something very, very different. It's an incompressible continuous liquid, right? Like water. Water is practically incompressible. It's an incompressible continuous liquid with a surface tension that we have in water as well, and it has friction. We also have that in water. So we assume it's like a syrup or something, or depending now what the eta, that's the coefficient of the internal friction is. And you assume that, therefore, it's called the liquid drop model of the atomic nucleus. So this is a substitution, right, which is utterly different. But to tell you the importance, the atomic bomb that was developed from 1938 on was based on the liquid drop model of the atomic nucleus, because you could show that these liquid drops, if you put in energy, then they start oscillating, and if the oscillation becomes too strong, then it can split up. This is exactly what happens in the atomic bomb, right? If you use nuclear energy, you have the same. You split the atom, you split the nucleus, and that can be wonderfully simulated by that. This was the basic for the atomic bomb. So it's not an unimportant toy model of some physics idiots who have nothing to do with reality. This was really important. So it's really important. So, and you can work with that model, and the corpuscular structure of the nucleus is thus substituted by a continuous liquid. And that this model was in place until the 1960s. Only then were people able really to put in the corpuscular structure in physics into the nuclear physics and understand the nuclei in terms of their components. It wasn't impossible before, and then they used that one. So it's an absolute standard procedure for physicists. They just use it. It's a substitution. Now, in a strict sense, this is not an approximation to the real situation. In the sense, namely, it cannot be improved by adding corrections. Because if you start with a liquid, you cannot add by corrections, make it corpuscular. It's just a liquid or not. It's a continuous liquid, no internal structure whatsoever, right? So you can't do that. So in a strict sense, this is not an approximation. It is a qualitatively counterfactual assumption. You assume that the nucleus consists of something completely different from what it is, completely false, completely counterfactual. You assume it's a liquid with certain properties. Nevertheless, physicists may call this substitution an approximation, right? Physicists speak that way. Yeah, we approximate the nature of the nucleus by a liquid. Yeah, that's an approximation. Fine. So no harm resulting. But I make the difference here because it's important. You'll see that. Now, physicists now accept such a model exactly for the reason that Friedman describes. That's very nice. If you look how Friedman describes, why do people accept, these strange models? It's exactly what Friedman says. The model is good enough regarding its prediction for the given purpose. This is what he says on page 15. Therefore, these unreal assumptions are okay. That's exactly what people say. The predictions from the liquid drop model were just fantastic. You could predict the atomic explosion. You can model that and then build the atomic bomb accordingly. And an alternative model that's predictively better is not available. And that was exactly the case in 1938 until the 60s. Only then, 20 years later, people developed predictively better models of the atomic nucleus than were available at that time. And for these 25 years, physicists were happy working with the nuclear drop model. It was wonderful, here you go, right? Exactly for the reasons that Friedman adduces. So, now, this is so far the discussion of assumptions referred to the material in sections 1 to 4, my discussion here, which Friedman denominated as abstract methodological issues. Remember, we had these 2 sections on assumptions, and there were abstract, he calls them abstract methodological issues with only little relation to economics, only this last example that he used with the firms. In section 5 now he turns, as the title says, to some implications for economic issues. So the real economic stuff is coming now after this abstract discussion, and as you see, I could illuminate the assumptions also of the second type, also with a physics example. So you could see this is much more general than just economics, but now come the things that are really specific for economics, and here we'll see some surprises. Now here in this section 5 now, Friedman discusses the special aspects of assumptions relevant in economics, and here we get final clarity on what Friedman means by assumptions in scare quotes. And most people who discuss Friedman do not take into serious account what happens in section 5, but they really concentrate in 3 and 4, and then because of Friedman's unclarity about these two types of assumptions, it looks completely confused, but it is not.